We interact with AI pretty much every single day, right? It's on our phones, in our work tools. We ask it to do everything from writing code to making art. But have you ever really stopped to think about how it thinks? I mean, what is actually going on inside that digital black box? Well, today we're going to find out. So here's a fascinating paradox for you. We see these AI models tackling incredibly complex problems, but at the same time, they can get totally tripped up by something as simple as a typo. It makes you wonder, are these things brilliant logical minds or just really fragile mimics? The answer, as it turns out, is kind of both. To really get this, we've got to pop the hood and take a look inside. We're going to unlock that black box and focus on a core piece of large language models that you've probably never even heard of. It's not the famous attention mechanism you hear about all the time. Nope, this is the secret ingredient that's quietly doing most of the heavy lifting. Say hello to the feed-forward layers. Seriously, while attention gets all the press, these layers are the real workhorses. They make up a staggering 2/3 of the model's parameters. The best way to think of them is as the AI's massive, searchable memory, a place where it stores every single pattern it's ever learned. And you know what? This memory system is actually incredibly elegant. Here's how it works. The AI sees a pattern in the text, and that pattern acts like a key. As soon as that key gets activated, the model pulls up the corresponding value, which is basically a prediction for what word comes next. So, for example, if the key recognizes the phrase every once in a, the value it fetches will be the word while. Simple as that. So if these layers are like a giant memory bank, what's actually stored in there? Well, it's not just a jumble of random data. Researchers dug in and found that these memories are like a huge library of patterns that we humans can actually understand. Let's look at a few. You can see right here the kinds of things the AI learns to remember. Some of them are pretty simple or shallow, like just recognizing that a sentence often ends with the word substitutes. But others are way more abstract and semantic. For instance, a key might fire up only when it detects a military context or a conversation about a TV show. It's like a library filled with books on both grammar and general knowledge. And this library is organized in a really sophisticated way. See, in the early or lower layers of the network, the AI is just focusing on simple, surface-level text patterns. But as that information flows up to the upper layers, the patterns it looks for become much more abstract. It's almost like the AI is learning letters first, then words, and then finally entire concepts. This quote from the researchers really just nails it. The AI's final answer, the word it spits out, isn't some single brilliant leap of logic. Nope, it's carefully built layer by layer by combining hundreds of these tiny pattern-matching memories, working its way up from the simple stuff to the really complex ideas. It all sounds incredibly powerful, doesn't it? I mean, an elegant, layered memory system that builds understanding from the ground up. But here's the catch. This entire sophisticated structure depends on one single, surprisingly fragile first step: how the AI actually reads the text we give it. And this, right here, is where we find its Achilles heel. Okay, so before an AI can do any of that clever pattern matching we just talked about, it has to read our prompt. It does this with a process called tokenization. Now, instead of seeing words or letters like we do, the AI breaks our text down into a sequence of predefined tokens. Just think of it like chopping up a sentence into a very specific set of Lego bricks that come from a limited kit. And this is where we run into what researchers call the curse of tokenization. Because the AI only understands its fixed vocabulary of tokens, its set of Lego bricks, it's super sensitive to anything it hasn't seen before, like a typo. It's totally blind to the fact that words themselves are made up of letters and have an internal structure. This slide shows the problem perfectly. The word assignment gets broken into two tokens, assign and meant. For us, the connection is obvious, right? But for the AI, these are just two totally different Lego bricks. The mathematical similarity between the whole word and its parts is practically zero. The AI just doesn't get that one is made from the other. Now, this isn't just some abstract, theoretical problem. This curse causes AI models to fail in ways that seem completely bizarre to us, because our brains don't operate on a fixed set of Lego bricks. Let's see what happens when we really put this to the test. Take a simple anagram. Unscrambling NAD to get AND is a piece of cake for a human. But for an AI, it's a massive challenge. Why? Well, because NAD and AND are probably completely different tokens, or combinations of tokens.
The AI doesn't see the shared letters, it just sees two different, unrelated items from its vocabulary list. And the data, as you can see right here, makes this crystal clear. For short words, a powerful model like Llama 3 gets it right maybe half the time. But look what happens as the word gets longer. Its performance just falls off a cliff. For words over 12 characters long, its success rate is less than 10%. The more characters there are to shuffle around, the less likely the jumbled result will match any of the tokens it knows. This is where you really see how a single typo can just shatter the whole system. Take the phrase largest underscore divisor. The model knows these tokens, but if you introduce just one typo, largest underscore divisor, the tokenization completely changes. That new garbled word is broken into a totally different set of Lego bricks, which makes it completely unrecognizable to the model's memory. The pattern it was looking for is just gone.
So this brings us to a really key finding. Research shows over and over again that these models are way more sensitive to character-level noise, typos, than they are to just reordering existing tokens. This points to a huge, fundamental difference between how machines read and how we read. We see the letters, they just see the tokens. Okay, so we've seen the elegant memory system and its super fragile foundation. The big question now is, can we actually fix it? Can we teach an AI to read more like a person and be a little less brittle? Well, the answer is yes, and the solution is pretty clever. One of the most promising techniques is called BPE dropout. What it does is, during the training phase, it randomly changes how words get tokenized. So one time, assignment might get split into assign and meant, but the next time it might be as, sign, and meant. This forces the model to learn that different combinations of its Lego bricks can still mean the same thing, which makes its understanding of words way more flexible. And the results really speak for themselves. As this chart shows, models that are trained with this BPE dropout technique consistently do better than the ones with standard, rigid tokenization. By basically making the AI's reading process less predictable, we make the model itself more robust and way more resilient to all the messy, unpredictable text it's going to see in the real world. Which brings us all the way back to our big question. After looking inside this black box, what's the verdict? Is this technology a brilliant pattern matching system, or is it a brittle reader that's just easily broken?
Well, the answer is it's both. Today's AI models are absolute marvels of engineering. They have this complex, layered memory system that finds and combines patterns in a way that is genuinely powerful. But all of that beautiful, elegant logic is built on the surprisingly fragile foundation of tokenization. And understanding that paradox, that it's both brilliant and brittle, is the real key to appreciating both the incredible power of AI and its current, very real limitations.